Welcome back to the theory of probability. So what we have been doing in our last discussion, we ended our discussion on defining the covariances and some of the basic properties of the covariances, which I am going to recall in a minute. But let me give the agenda maybe for the today's discussions actually. So what we are going to focus today is basically on developing the theory, basic theory of the conditional expectations. Okay. So we have kind of defined the conditional probability distributions, PDFs and CDFs. Okay, so now we're going to move towards what you call the conditional expectations. We're going to do different examples, some of the basic properties of it, and then we next want to attack what you call the theory of the moment generating functions actually. So it's a wonderful set of ideas which basically allow you to compute the expectations of the different kind of random variables through differential calculus actually. So we're gonna attack those as well, and maybe then in the end, if there will be a time, then maybe we can go to the weak law of large numbers and central limit theorem. Okay. Central limit theorem. So we'll see that. Okay. Out of all this stuff, what stuff we can cover actually. But probably the next lecture would be the last lecture of this set of discussion on theory of probability basically. So what I'm planning basically, that I'm planning to do that lecture also in this week and post both lectures on YouTube, and then post a set of exercises, and then maybe in the first week of the July or in the second week of July you will face an exam of the theory of probability. So this is a little bit of agenda today. So now let me recall what do you call covariances. So we talked about covariances last time, that okay, if you have two random quantities and two random processes, you want to know that how these processes are related with each other. Okay, so in other words, that are they kind of related in the sense that if one is increasing in its value, the other is increasing, or if one is increasing, other is decreasing, or they are unrelated actually. So the covariance is a way to tell that how two random variables are related with each other actually. And then we know that we defined the covariances at, we deduced basically that the covariance of random variables x, y can be computed as the expectation of x, y minus expectation of x times the expectation of y. And then we proved some of the basic properties of the covariances. We said that if x and y are independent, then the covariance of x and y should be what you call 0. But the converse is not true. So if the covariance of two random variables is 0, it is not necessary that the random variables are independent of each other. Then we kind of proved a proposition, okay, which tells us that the covariance is kind of a symmetric operation. The covariance of xy is same as the covariance of yx. And then we also said that the covariance is kind of a two-dimensional analog of variance. So if you compute the covariance of xx, you're going to get what we call the variance of x, which is which indeed follows from here. So if we substitute y equal to x here, so this will become expectation of x squared minus expectation of x whole square. We also proved that if you have the covariance of say ax y, then this is same as a times of the covariance of xy. In other words, that you can pull out the constant out of the covariance actually. And then the final interesting identity that we kind of proved was that if you have to compute the covariance of the sum that say goes from 1 to n of the random variables, which is sum of some random variables I equal to 1 to n and some other random variables say j equal to 1 to m, what you call yj, then this sum is really equal to the double sum that goes like I equal to 1 to n and j equal to 1 to m covariances of xi yj. Okay, so kind of linearity property that okay, the covariances of the sums is the sum of the covariances actually. Okay, so we also deduced that, and then we also proved an interesting relationship between the variances of sum of the random variables. We know about the expectations that if you compute the expectation of sum of random variables, okay, no matter what random variables you have, this is same as computing the sum of expectation of each, individual random variables actually. But is it true for the variances? The answer is no actually. The variances of the sum that goes from I equal to 1 to n xi, we kind of shows that this is same as the sum that goes from I equal to 1 to n, the variances of say xi plus the twice of a double sum on the two indices I less than j of the covariances of xi and xj. In other words, the variance of xi is equal to the sum of variances of xi plus twice of the all possible covariances of the pairs of xi's actually. Okay, so in other words, take these xi's, if you are able to make as much as pairs, okay, okay, so the variance of the sum is the sum of the variances plus twice of the covariances of all possible pairs xi and xj. In other words, for example, if I say that the variance of what is x1 plus x2 plus x3, then this is same as the variance of x1 plus variance of x2 plus variance of x3 plus twice of the covariances of the all possible pairs that you can make out of it. So x1, x2 plus twice of the covariances of x1, x3 plus twice of the covariances of x1, say x2, x3. Okay, so this is what is going to be. So you might think that why not there is covariance of x2, x1. I mean, there is covariance of x2, x1, but since covariance is symmetric, that covariance is added in this 2 actually. So in other words, this why you have this 2, because one covariance pair is going to be covariance of x1, x2, another is going to be covariance of x2, x1, but since these both are equal, so their sum would be the twice of the covariances of x1, x2. Okay, so this is what we proved in our last discussion, and we also proved actually that if say these xi's, this x1, x2 up to xn are independent, then you have this property that the variance of the sum I equal to say 1 to n xi is equal to the sum of the variances that goes from I equal to 1 to n variance of xi. Why this would be the case? This is the case because if the two random variables are independent, their covariances are equal to 0. So since their covariances are equal to 0, so all these terms, in other words, all these terms would be what you call 0, and hence the variance of xi is going to be equal to the variance of sum of xi's actually. So I hope that this stuff is making a little bit sense to you. Now let's do some examples and a little bit of calculations say based on it actually. Okay. And then move to the next topic actually. For example, imagine you have, so this is the example for A from the Ross. For A from the Ross. So what we have is that, say, so say you have this n random variable, so you can treat that this is the some piece of information, some random data. Okay, so you have these n random variables which are independent and identically distributed actually. Okay, so they are independent and identically distributed. That is that the expectation of xi is a fixed number and the variance of xi is also, say, fixed actually. Okay, so these two numbers are fixed for all these, and they are independent as well. So in other words, you take x1, x2, x1, x3, all possible pairs are basically independent of each other. So all of these are independent. Now, if you take, say, x bar as the average of this random data, then average can be computed what we call the sample average actually. So if this is a sample, okay, then the sample average is I equal to 1 to n xi divided by what you call n actually. Okay, and the sample deviation, the quantity is xi minus xi bar. Okay, so xi minus xi bar, you call these quantities as that these are sample deviations from average actually. So these are the sample deviations from average. Now we define the sample variance of these n initial data as this formula. So you know from it, from your basic statistics courses actually, that the sample variance is a random variable as a square that goes like sum of the x minus xi minus x bar square divided by n minus 1. So you call this quantity as what you call the sample variance. Okay, you call the sample variance. Now what you have to do, okay, so you have to compute is the variance of this sample average. Okay, so this is the first thing that you need to compute, and the second thing that you need to compute is the expected sample variance. Okay, so the expectation of sample variance. So these are the two quantities that you need to compute using the properties that you have here. Now, here is the first quantity. So what would be the variance of x bar? So the x bar is sum of I equal to 1 to n xi and everything divided by n. Now we know the property of the variance is that the variance of ax is equal to a square times of variance of x actually. In other words, that if you pull out the constant, then the variance is going to be really 1 over n squared times the variance of, so 1 over n squared times the variance of this sum. But the sum of the variances is this formula actually. So the sum of the variances of sample mean is this formula. So this would be equal to the sum I equal to 1 to n variances of xi. Okay, plus the 2 times of the covariances of xi and xj. So now we know that all of these xi's and xj's are independent of each other. So these covariances are all going to be 0. So this is going to be the variance of xj. Now if you substitute the variance of xi, which is fixed for all constants, so it's going to be sigma squared. So it's like 1 over n squared and summing up the same number I equal to 1 to n sigma squared actually. So you have this one number sigma squared being summed n times actually. So this is going to be n sigma squared by n squared. So the outcome is that, okay, you take your sigma squared and divide it by the sample size actually. Okay, so the variance of the average is basically that, okay, take your variance, okay, the common variance, and divide it by the sample size actually. Okay, divided by the sample size. So this would be the variance of x bar, and similarly you can also compute say the expectation of the variance. So let's compute say expectation of sample variance.